Okay, so we have seen already how to figure out the eigenvalues for a matrix, and what we're going to see for this module is the ideas in your textbook on how to find the eigenvectors corresponding to a fixed eigenvalue. So now that you know how to find the eigenvalues, suppose that we have so assume that we know that lambda, this is now a fixed number, a scalar, is an eigenvalue for A. So just a little bit of the things that your textbook tells you. So I know that that means that A times some vector that we're trying to figure out, my eigenvector, is going to satisfy that this is lambda times that vector. Now, what you have in this right-hand side is a scalar times a vector. So we kind of want to transform this into a matrix computation so we can kind of manipulate these matrices. So what we do is I'm going to put here the identity matrix because the identity times x gives me the identity matrix, and then I can move this to this side and factor it out. So if I do that, I will get A minus lambda times identity, all of these multiplied by my vector x. Now this is going to be variables because I don't know my eigenvector, so this works as a variable, a set of variables or unknowns. This should be equal to the 0 vector. And this is where this technique comes from. So if I'm trying to figure out what are the eigenvectors corresponding to a known lambda, then my steps are going to be, well, first I want to get the extended matrix . A minus lambda I, and remember I'm going to times x equals to 0, so I am going to extend it equals to 0, and then just solve this system, and that means that I'm going to just row reduce it to find the solutions. So let me continue with the same example that we saw before. So in that example, my matrix A was a matrix 1, 0, 0, negative 4, 5, 4, and negative 2, 2, and negative 2. For those, we have figured out all the eigenvalues. The eigenvalues that we got were 1, negative 3, and 6. So let's try to figure out what are the eigenvectors for lambda equals negative 3. Okay, so the first thing that I'm going to do is I'm going to do A minus lambda, so minus negative 3 times identity. And again, because negative 3 times identity only affects the diagonal, this is going to give me the same matrix that I have here, but in the diagonal, I'm going to do plus 3. So that will give me 1 plus 3, that gives me 4, 5 plus 3 gives me 8, and minus 2 plus 3 gives me 1. And then everything else in my matrix is going to be as before. So let me just point it out here. That's the only change. And everything else is the same. So 0, 0, negative 4, 4, negative 2, and 2. Okay, so what I'm going to do is now I'm going to extend it with a 0 here. So let me do that here. And that means that I'm going to erase this one. I'm going to extend it with 0, 0, 0. And I'm going to solve this system. Remember, my first column corresponds to x1, the second for x2, and the third column for the coefficients of my variable x3, which are the entries for my generic eigenvector. So what do? I, of course, need to get a 1 here, and that's easy. If I do 1/4 times row 1, I will get 1, 0, 0, 0, -4, 8, 4, 0, -2, 2, 1, 0. And using that, I'm going to make the other ones 0. So using this, I'm going to make this and 0. And again, that's easy to see. That's going to be 4 times row 1 plus row 2 goes to here. And then 2 times row 1 plus row 3 is going to be my new row 3. So you know how to do this. So I'm giving you a little reminder of that. So I end up getting my usual 1, 0, 0, my original one. Then in the second one, I'm going to get 0, 8, 4, 0. And in the last one, I will get 0, 2, 1, 0. Then I want to have a 1 in this entry, and it's easier for me to just switch these two. So I'm going to do row 2, is switch to row 3, row 3. And I get 1, 0, 0, 0, 0, 2, 1, 0, 0, 8, 4, 0. And then once that I have that, again, I want to have a 1 here in this entry. So to have a 1, I'm going to do 1/2 row 2, 1, 0, 0, 0, 0, 1, 1/2, 0, 0, 8, 4, 0. If you see, I already have a 0 here, so I only need to convert this into a 0. So I do -8. Go back here. -8 times row 2 plus row 3. And I end up getting my matrix 1, 0, 0, 0, 0, 1, 1/2, 0. You can already see that this is going to give me actually zeros. I'm done because I cannot get a 1 here. This is already reduced. And that means that I can just read my solutions out of this. So let's see. Remember that we said that these were my coefficients for x1, x2, and x3 respectively. So if I read that, what this tells me is that x1 is equal to 0. And then I also have from the second line 1 times x2 plus 1/2 x3 is equal to 0, and the last row doesn't give me any new information. 0 equals to 0, which is fine. So the last thing that I need to do is just organize this in a way that I can see vectors out of that. So one of the things that might be helpful is, and I'm just going to do what you have in your textbook again, just to so you can see where that comes from, is instead of solving for x2 in terms of x3, which you can totally do, I can just solve for x3 in terms of x2 because that just gives me integers. So if you solve for x3, what you have is that x3 is equal to -2x2. Okay, so what do I have as my solutions? My solutions for x, that is going to be some entries x1, x2, and x3, are going to be x1 is 0, x2 is equal to x2, And given this last one, x3 equals negative 2x2. And once that I have this, what I can do is I can just factor out that x2. So x2 is multiplying the vector 0, 1, and negative 2. Okay, this tells me that one of my vectors is going to be given when x2 is equal to 1, but there are actually many solutions to this system of equations. Each of the solutions is actually an eigenvector. And that makes sense because actually eigenvectors form, eigenvectors will always give you not just a unique solution, but a set of infinite solutions. So for any value of x2 that you can think about, so different than 0, let me write that here. Those are going to give you eigenvectors. So an eigenvector would be 0, 1, negative 2, or if x2 is equal to 2, you would get 0, 2, negative 4, and so on. As many as scalars that you can substitute for x2, those will give you all the possibilities for the eigenvectors corresponding to the eigenvalue negative 3. And that's it. So let me just label this. These are all the eigenvectors. In your questions, in your problems that you have to solve for your quizzes and exam, some of the questions are just asking you to come up with these equations, and these are the kind of things that you're going to check in the options for solutions. So once that you're here is just like trying to write it as a vector, but this part you're also being tested on that on our problems, group of problems. And that's it.